Welcome back to the third part of our module on energy enzymes and thermodynamics. And what we're going to look at in this section is how the energy in molecules changes as a reaction proceeds. And that'll lead us into a discussion of some enzymes. There's my phone. Let's turn that off. Okay, so let's go back to our equation that describes cellular respiration. Glucose in the presence of oxygen is converted by cellular respiration to water and carbon dioxide. And I've put in the top left-hand corner, I think it's up there, the graph that shows us how we start off with a large amount of energy in glucose and oxygen, and we end up with a smaller amount of energy in carbon dioxide and water. And the energy that's come out of these sets of reactions is harnessed by your cells and used to synthesize the molecule ATP, which is the energy currency in the cell. So, as what we're going to look at now is how energy changes as a function of those reactions occurring over time. And that's what the other graph shows here, the line graph. So we can show this with a bar graph, which we'll be doing so far. But if we want to look at how energetics change as a consequence of reactions proceeding, then we can use a line graph. So what we've got here is on the y-axis is G, free energy, also known as Gibbs free energy, which is where the G comes from. So that's Gibbs free energy. And then on the, along the x-axis, we've got the reaction proceeding. And so here on the left of the graph, that would be the start of the reaction. And over here would be the end of the reaction. We know this is start because we've got reactants, and we know this is end because we've got products. Now, what's really important with these graphs that we're going to look at in this section is that you don't put time on that bottom x-axis. It's the start and the end, and we're not making any conclusions or any inferences about how fast things are happening. We're not talking about speed, we're talking about change in energy. So what's going to happen is that we're going to start off with a certain amount of energy in the reactants, glucose and oxygen, and we're going to end up with a certain amount of energy in the carbon dioxide and the water. And so the difference between the energy in the products and the energy in the reactants is a value called delta G. Now, that sounds complicated. Delta, the Greek letter delta, is just used in science to indicate change or difference. And so delta G is just the difference in energy when you look at the product's energy and the reactant's energy. So as the reaction proceeds, and this is, bear in mind, this is a whole set of many reactions, as we move through these reactions, thinking about them more globally, the first thing that happens is you've got to put some energy into these reactions, and so there's this energy investment that has to happen. Now, by the time we reach this point up here, is what happens is the rest of the reactions occur spontaneously on their own, and so here we've got to put work in. So this is energy going in. I mean, think about what's happening. The y-axis is going up until we reach this point, and then energy is coming out, and we get down to the products. So we're harnessing all of this energy that's coming out in the process of cellular respiration, but cellular respiration has got to put this energy in as well. So this has to be done, this work has to be done, but once we reach this point here, then we can harness all this energy. So the energy that comes out, that's the difference between the top of the peak and down here. So that difference is what we get out. Now we've put that much in, and so as what we see then is that this value for delta G is a number less than 0, and we'll calculate that number in a moment. So that number is less than 0, and that's going to become important in a little bit. Now let's look at the reverse process. And so the reverse here is going to be you combining water and carbon dioxide to make glucose and oxygen, and that's photosynthesis. So if we get energy out of cellular respiration, then we're going to have to put energy into photosynthesis, and that's energy in the form of sunlight, or non-natural light as well, I guess. So it's the same graph. We've got the same y-axis, the same x-axis, reactants at the start, products at the end. So we've got to put energy in. Any energy is going in, still going in, still going in, still going in. Now we've reached this point, and then we'll actually get this much back out. But as what you see is we put all of this in and only got this little much out. And so when we do the calculations for this, we see this value for delta G is greater than 0. So those are two sets of reactions that we've looked at so far. Cellular respiration, which is breaking things down, is going to have a negative delta G, and reactions like photosynthesis, or collections of reactions like photosynthesis, are going to build things up, and they're going to have a positive delta G. Now this makes sense because this means we're putting energy in. If we build something, we're doing work, energy's got to go into that. When things get broken down and new products are formed from those breakdown products, then we get energy out and we can harness that to do work in cells. Okay, so let's look at calculating this value delta G. It's actually pretty simple. There's a complicated way of doing this. We're not going to do it. If you want to calculate delta G, all you do is you take the G in the reactants and you subtract it from the G in the product. So the equation of delta G is equal to G in the products minus G in the reactants. So if I told you what G for the products was and what G for the reactants was, you can subtract one from the other and get delta G. You've got to remember it's products minus reactants. People always get this the wrong way around and end up with the sign of delta G completely wrong. So let's look at this equation here. It doesn't matter what the reactants are. A is a reactant, B is a reactant, and those are reacted together and converted to the product C plus D. So let's say that the amount of free energy available in A and B is 165 kilocalories per mole. And this is just the units for G. Kilocalories per mole. It's an amount of energy, basically calories, in an amount of the substance. And here we're using a mole, which we talked about before. If we say that the G value for C plus D, the products, is 112 kilocalories per mole, then it's pretty easy for us to work out what delta G is, because it would be G in the products, which is 112, minus G in the reactants, which is 165, and we end up with 112 minus 165. Now, so what we're doing there is a smaller number minus a bigger number, and so that gives us a negative number. And so the negative number is confusing. Negative 53 kilocalories per mole. People look at this and they say, well, how can you have a negative amount of energy? The sign here is telling you about directionality of change. So it's not there's a negative amount of energy. Unless we're getting some weird Star Trek stuff, I'm not sure we can add anti-energy at this point. So delta G here is a negative number. So what does that number actually mean? Well, it's got a negative sign, that has meaning, and it's got a magnitude, 53 kilocalories per mole. So the difference in energies between the products and the reactants here is 53 kilocalories per mole. That's the absolute difference. The negative symbol tells you that what you finish with is less than what you started with. A and B has got more than C and D. That's what that tells you. So what do we do with that? How do we interpret that? What does that value mean? So here are those two graphs that we looked at just now. We've got the graph over here on the left for cellular respiration and the graph over here on the right for photosynthesis. So if we have a situation where the reactants have more G than the products, we get this value of delta G is less than 100. Now, if you don't believe me, put any number for reactants, which is bigger than a number for products. Make this 100 and make this 20. 20 minus 100 is minus 80. Minus 80 is less than 0. Some people say, well, minus 80 is just a smaller number than 0. It's a negative number, okay? It's a number less than 0. So delta G here is less than 0. So what that means is that when that sign of that delta G is negative, when you've got a number less than 0, a negative delta G, that means the reaction is exergonic. That means energy will be released, and we can then harness that energy, in the case of cellular respiration, and use it to do work. Now, some people say this is they talk about exothermic, and we're not going to do that because that's what happens in physics and chemistry when heat is released. Exergonic, here we're talking about energy that can be released and harnessed to do work. So here, energy is going to come out. How much is going to come out? Well, it is this here less this here. That's what that value delta G being less than 0 is. Now, in an endogonic process, think about it. This is photosynthesis, for example. If we're going to build things up and we're going to make things less random, if we're going to decrease entropy like we would be doing if we were building things up and making them more random, giving them less freedom of movement, less degrees of freedom of places they can occupy in space, we've got to put energy in to do that. That's work. And so energy's got to go in. And so delta G for that process is going to be greater than 0. These processes are endogonic. Endo meaning to go in, exo meaning to come out. So here we've got reactants low G, products high G. We've got to put all of this energy in, okay? And we get a little bit out here. You always get some out, but what we get out is much less than what we put in. Okay, so here, put some numbers on here if you don't believe me. People don't believe this when we talk about it. Let's make this 100 and this 30. 30 is less than 100, so it works on the graph. So 100 less 30 is 70, so delta G is greater than 0. That reaction would be endogonic. So what I can do is I can give you values for G in the products, G in the reactants, and you can calculate delta G and then make some conclusions about the reaction. Now, people always say, well, what can I learn about the speed of the reaction from delta G? Absolutely nothing. You can't learn anything about the speed of the reaction from delta G, and we'll look at that and why that is when we look at enzymes a little bit later. Now, so what we're going to do now is a whole bunch of questions. I think I'm counting 8 questions that we're going to go through here. So I'm going to go through them. If we need to stop and chat about them, I will. If not, I'm just going to keep going and I'll flash the answer up on the screen. Here comes the first one. Let's see how you get on with this one. Here we go. Okay, let's just talk about this one real quick because it's the first one, and then we'll do some, and I'll just sit quietly. Okay, so the reactant is molecule A, 100 kilocalories per mole. The product is molecule B with 20 kilocalories per mole. What's the change in free energy as A is converted to B? B is the product minus A the reactant. So B is 20 minus 100. 20 minus 100 is minus 80 kilocalories per mole. The answer there would be C. What do I learn from that reaction? I learned that that's an exergonic reaction. Another word that people use to describe exergonic reactions is spontaneous. Once you get them going, they will go to completion at their own speed. Many reactions are spontaneous. They just go very, very slowly. So C. Okay, here comes the next one. Let's take a look at this one. It's a hard one, but I'm going to leave you to do that on your own. Here comes the next one. Now this is just a different way of asking the same thing, so you've got to think about it carefully and put the answer on the screen. Here comes the next question. Okay, let's talk about this one. P is converted to Q. The change in free energy as P goes to Q is minus 200 kilocalories per mole. So let's just think about that situation to start with. P goes to Q, and so is what that means with delta G being negative. Is what means is that the reactant P must be up here, and the product Q must be down here. That's the only way I can get a negative number, is to have a small number here and a big number here. So that's kind of what we're looking at in terms of the G values. So what do we have then? More free energy is released from the formation of Q from P than would be required to convert Q back to P. Okay, so let's think about this. P starts here, and we end up with Q down here. So let's not worry about how we get from here to here. But as we go from here to here, that amount of energy comes out. The difference in the two G values, whatever those would be, that gives us minus 200, that's what will come out of the reactions that convert P to Q. If I want to convert Q back to P, I've got to put in exactly the same amount of energy. I've got to do no more work, and I've got to do no less work. I've got to do exactly the same amount. So if you go from P to Q, if you want to go back from Q to P, exactly the same amount of energy. So this would be false. Here comes the next one. Okay, here comes the next one. Okay, we've got 2 left, and then we'll wrap it up for this video. Okay, and then last but not least, make sure you check out the axis on this graph because it looks the same, but it's a little different. Okay, so what we've done here is we've looked at how energy changes as reactions or groups of reactions proceed. So at the end there, we introduced the idea also of what we can conclude if we're told about the entropy. So you might have to step back and look at the relationship between free energy and entropy. Let's just summarize it really quickly, and you can go back if you need to. If a molecule has a high amount of free energy, its molecules, its atoms, its component parts are not randomly ordered. Okay, but if we have something which has got a low G value, like carbon dioxide and water, those molecules have more randomness in their organization and therefore a higher entropy value. So low G, high S, high G, low S. From that, you can probably work out a lot of the answers to those questions. We'll wrap it up there. I'll see you next time.